to stoichiometry?
Who?
What?
When?
Why?
Before we proceed to the calculations, let us first have a brief introduction about the mole concept. So the mole concept was created by general chemist Wilhelm Oswald.
Mole concept, a term used to describe the amount of substance, is equals to Avogadro's number, which is equivalent to 6.022 times 10 raised to the power of 23 particles, atoms, or molecules of substance.
The term was first used around 1896.
The purpose of this term is so scientists can know exactly how many atoms or molecules are reacting together and what product they form.
All about mole denotes a collection of large fixed numbers of atoms or molecules. Abbreviation for the unit is mole, amount of substance containing the same number of atoms as 12 grams of pure carbon. Avogadro's number, N is equals to 6.022 times 10 raised to 23 atoms or molecules or mole of substance.
Anatomy of a chemical equation. A chemical equation consists of the chemical formulas of the reactants on the left and the products on the right. The two are separated by an arrow symbol, usually read aloud as yields. Each individual substance's chemical formula is separated from others by a plus sign. The state of matter of each compound or molecule is indicated in subscript next to the compound by an abbreviation in parentheses. For example, a compound in the gas state would be indicated by G, solid as S, liquid as L, and aqueous as AQ. Aqueous means dissolved in water. It is a common state of matter for acids, bases, and dissolved ionic compounds. As an example, the formula for the burning of methane can be written as follows. This equation would be read as CH4 plus 2O2 yields CO2 and 2H2O. For equation involving complex chemicals, read the chemical formulas using AUPAC nomenclature rather than reading the letter and its subscript. Using AUPAC nomenclature, this equation would be read as methane plus oxygen yields carbon dioxide and water.
This equation indicates that oxygen and CH4 react to form H2O and CO2. It also indicates that 2 oxygen molecules are required for every methane molecule, and that the reaction will form 2 water molecules and 1 carbon dioxide molecule for every methane, and 2 oxygen molecules that react. The equation also identifies that all the compounds are in the gaseous state. The stoichiometric coefficients, are the numbers in front of the chemical formulas, result from the law of conservation of mass and the law of conservation of charge. Also, note that as in the mathematical commutative property of addition, chemical equations are commutative. Reactants and products can be written in any order, provided that they are on the appropriate side of the reaction arrow.
Subscript tells the number of atoms of each element in a molecule. As you can see in the chart, the example H2O, hydrogen has a subscript of 2, which means it has 2 atoms, and oxygen has an imaginary subscript that is equivalent to 1 atom. Same to the second example, where oxygen has a subscript of 2, which means it has 2 atoms. Coefficients tells the number of molecules of compounds. So the example in the chart, H2O has a coefficient of 2, which means that is the number of their molecules. So basically, we just need to multiply their subscript to the coefficient to get the numbers of their atoms.
Combination reaction. 2 or more substances react to form one product.
Solving combination reaction. Combination reaction involves combining 2 or more substances to produce one substance. For example, here is N2 gas reacting with 3H2 gas to produce 2NH3 gas. In this equation, we already predicted and balanced the equation. But let me show you how to predict and balance this equation. First, you need to combine nitrogen gas to hydrogen gas. So you will have NH3 gas as the product. Since the equation is not yet balanced, you need to put 3 coefficient here and 2 here, and that's it. The equation is balanced. For the next example is C3H6 gas reacting with Br2 liquid to produce C3H6Br2 liquid. Just like the first example, I'll show you how to get this. So you need to combine carbon, hydrogen gas, and bromine liquid, so the product will be C3H6Br2 in liquid state. We write L in this, not G, because according in phase transition, gas to liquid is called liquefaction. Since this equation is already balanced, there is no need to balance it. And for the last example, we have 2MgS reacting with O2 gas to produce 2MgOg. Just like the other two examples, we predict the product and balance the equation by combining magnesium and oxygen. So the product will be MgOg, and we balance the equation by putting 2 coefficient here and 2 here. And that's how to predict and balance equation in combination reaction.
Decomposition reactions. One substance breaks down into 2 or more substances.
Solving decomposition reaction. Decomposition reaction is the opposite of combination reaction. With that, we just need to break down the single compound into 2 or more simpler products. Example, we have here CaCO3S producing CaOS and CO2 gas. So since in this equation, we already predicted the products and the equation is already balanced. So I'll show you how to predict its product and balance its equation. First, you just need to decompose this to get the product. So we will have CaOS and CO2G as the product. And since the equation is already balanced, there's no need to balance it. For the next example is 2KClO3S producing 2KClS and 3O2G. Just like the first example, I'll show you how we predict and balance the equation. First, we decompose this and we will have KClS and O2G. We need to balance the equation, and we do it by putting 2 here, also 2 here, and 3 here. The equation is balanced, so that's how we predict and balance the equation. And for the last example is 2Na and 3S producing 2NaS and 3N2G. We can predict the product by decomposing this one. And we'll have NaS and N2G as products. And we can balance this equation by just putting 2 coefficients here and 2 here, and also 3 here. And that's how you can predict and balance equation in decomposition reaction.
Reactions. Rapid reactions have oxygen as reactant, sometimes produce a flame. Most often involve the hydrocarbons reacting with oxygen in the air to produce CO2 and H2O.
Solving combustion reaction. Combustion reaction most often involve hydrocarbons reacting with oxygen to produce carbon dioxide and water. Here are some examples of combustion reaction and I'll show you how to solve it. First example is H4 gas reacting with 2O2 gas to produce CO2 gas and 2H2O gas. As you observe, this equation is already predicted and balanced. So I'll show you how I get this. Since the equation involves hydrocarbon reacting with oxygen, the product will be carbon dioxide gas and water. And we need to put two coefficients here and 2 here to balance the equation. Next example is C3H8 gas reacting with 5O2 gas to produce 3CO2 gas and 4H2O gas. Just like the first example, I'll show you how to get this. We just need to balance the equation since it involves hydrocarbon reacting with oxygen. So the product will be CO2 and H2O gas. And we need to put 5 here and 3 here and 4 here to balance the equation. And for the last example is 2H2 reacting with O2 to produce 2H2O. Just like the other two examples, I'll show you how to get this. Since it only has a hydrogen reacting with oxygen as a reactant, the product will only be H2O. And we need to put 2 coefficients here and 2 here to balance the equation. And that's how to predict and balance the equation in combustion reaction.
What is the AMMO unit? Defined since 1961 as 1/12 mass of 12C isotope, wherein 12C is equal to 12 AMMO. Formula weight, or FW, is the sum of the atomic weights for the atoms in a chemical formula. So the formula weight of calcium chloride, or CaCl2, would be Ca 1 times 40.1 AMU plus Cl 2 times 35.5 AMU is equivalent to 111.1 AMU. These are generally reported for ionic compounds.
So sodium chloride is an ionic compound, and sodium hydroxide is also ionic. So if you ever have to calculate the molecular weight, formula weight, atomic weight, molar mass, the procedure is the same. You're using the periodic table and you simply have to add the numbers, add the atomic masses of all the elements. So go ahead and calculate the formula weight or molar mass of these two ionic compounds. So for NaCl, we simply need to add the atomic mass of sodium and chlorine. The atomic mass for sodium is 22.99. Sometimes you can round that to 23. And for chlorine, it's about 35.45. So if we add the two numbers, you should get 58.44 grams per mole. So 1 mole of sodium chloride has a mass of 58.44 grams. Now what about sodium hydroxide, NaOH? So we have 1 sodium atom, 1 oxygen, and 1 hydrogen. The atomic mass for oxygen is 16, and for hydrogen it's 1.008. So we just gotta add these three numbers. And you should get 39.998, which you could round it to 40 if you want, grams per mole. So that's the formula weight for sodium chloride and sodium hydroxide, which is the same as
molecular weight, or MW, sum of the atomic weights of the atoms in a molecule. For the molecule ethane, C2H6, the molecular weight would be C2 times 12.0 AMU plus H6 times 1.0 AMU equals to 30.0 AMU.
CO2. All you need to do is add up the atomic weights of each element. So we have 1 carbon and 2 oxygen atoms. the atomic weight for carbon, you simply need to replace C with 12.01. And the atomic weight for oxygen, according to the periodic table, it's approximately 16. 2 times 16 is 32. And if you add 12.01 to it, you should get 44.01. This is the molar mass, or also known as the molecular weight, since CO2 is a molecule. And it has units grams per mole. So that's the molar mass of CO2. So what this means is that 1 mole of carbon dioxide has a mass of 44.01 grams. Molar mass is the mass of 1 mole of a substance. Let's try some more examples. The molar mass for methane, CH4, and ammonia, NH3. So in methane we have 1 carbon and 4 hydrogen atoms. The atomic mass for carbon is 12.01, and the atomic mass for hydrogen is 1.008. So 4 times 1.008, that's going to be 4.032. And if we add 12.01 to it, this is going to give us a molar mass of 16.042, and the units is grams per mole. Now let's do the same for ammonia, NH3. So we have 1 nitrogen atom and 3 hydrogen atoms. Nitrogen has an atomic mass of 14.01, and for hydrogen we already know that it's 1.008. So 3 times 1.008, this should give you 3.024. And then if we add 14.01 to that, you should get the molar mass for ammonia. And that's about 17.034. So you can also call it the molecular weight.
Percent composition. One can find the percentage of the mass of a compound that comes from each of the elements in the compound by using the equation. The percent of element is equals to number of atoms multiplied by atomic weight all over FW of the compound multiplied by 100.
2011, sucrose. Let's calculate the percent by mass of carbon. Now the first thing I would recommend doing is finding the molar mass of the entire compound first. So let's do that. We have 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. Carbon has an atomic mass of 12.01, and hydrogen is 1.008. Oxygen, 16. So if you type this in exactly the way you see it in your calculator, you should get 342.296 grams per mole. So that's the molar mass of the entire thing. Now, if you want to find the percent by carbon, you need to take the molar mass of all 12 carbon atoms and divide it by the total, and then multiply by 100%. So each carbon is 12.01, that's the atomic mass. The total molar mass is this number that we have, 342.296, and then we're going to multiply it by 100%. So 12 times 12.01, that's 144.12. Divide that by 342.296, and then take that result, multiply by 100%, and you should get 42.1%. So that's the percentage by mass of the carbon atoms in sucrose. Now I'm just going to rewrite the answer on the top so we can reference it later. So it's 42.1%. Now let's do the same thing with hydrogen. So we need to take the mass of all the hydrogen atoms. There's 22 of them. Each has an atomic mass of 1.008, and divided by the same total mass for the entire compound, which is 342.296. And then multiply everything by 100%. So 22 times 1.008, that's 22.176. And then divide that by 342.296. And then multiply by 100. This will give you about 6.5% if you round it. Now let's do the same thing with oxygen. So in sucrose, there are 11 oxygen atoms, each with an atomic mass of 16, then divided by the total molar mass. 11 times 16, that's 176. And then divided by the molar mass and multiplied by 100, you should get 51.4. So that's the percent by oxygen, or the percent by mass of oxygen. Now if you add up 51.4, 42.1, and 6.5, this will give you 100%. That's how you can tell if you did everything correctly.
Atomic mass unit and the mole. AMO definition is 12 carbon is equals to 12 AU. The atomic mass unit is defined this way. 1 AMO is equals to 1.6605 times 10 raised to the power of negative 24 grams. How many 12 carbon atoms weigh 12 grams? 6.02 times 10 raised to the power of 23. 12 carbon weigh 12 grams. Avogadro's number, the mole. Number of atoms is equals to 1 atom over 12 AMO multiplied by 1 AMO over 1.66 times 10 raised to the power of negative 24 gram times 12 gram is equals to 6.02 times 10 raised to the power of 23. 12 carbon weigh 12 gram.
Molar mass, the trick. By definition, this is the mass of 1 mole of a substance, that is, grams over mole. The molar mass of an element is the mass number for the element that we find in the periodic table. The formula weight in amos will be the same number as the molar mass in grams over mole.
Mole provides a bridge from the molecular scale to the real-world scale. The number of moles correspond to the number of molecules. 1 mole of any substance has the same number of molecules.
Mole relationship. 1 mole of atoms, ions, or molecules contains Avogadro's numbers of those particles. 1 mole of molecules or formula units contains Avogadro's number times the number of atoms or ions of each element in the compound.